So good morning. So wonderful. I have 7 students here. Let's start. Last time we started to discuss molecular spectrum. So it's a very powerful method and probably the most effective method in determining various properties of a molecule. So last time we started off with the full expression of the energy or the allowed energy of a molecule. So we have this electronic energy, usually is the bottom of the binding curve. So it's just a number. Then we have this vibrational energy term that has to do with the nuclear vibrational motion. Then we have this rotational energy term that is related to something like 2 balls with a rod. And then for diatomic molecules, it's a linear molecules, so it could rotate. The rotational spectrum usually appears in the microwave range. And here is an example that we discussed last time. This is carbon monoxide. You see rather regularly spaced peaks appear in the absorption rotational spectrum. And we also discussed that by reading out or measure the spacing between these regular peaks, it is related to the moment of inertia, or it should be 1 over the moment of inertia, and from which you can extract the bond length. So it is a very useful experimental technique. There's a selection rule, of course, but it is electric dipole type physics behind it. Therefore, it is similar to what we discussed in atoms. The requirement is that the molecule must have a permanent electric dipole moment. Then we moved it on to discuss vibrational spectrum. This usually has to do with infrared range. The physics is about molecules making transitions to the ground from the ground state of the vibrational level n equals 0 to some excited state, usually n equals 1. At room temperature, as the TA showed last week, basically all molecules reside in the vibrational ground state. So if you shine in some infrared, then the molecules could absorb and then go to this n equal 1 state. Now, depending on the resolution of your experiment, you may just see some signal related to this energy difference if the resolution is weak. But if the resolution is higher, then you may actually see from which rotational state belonging to n equals 0, the transition goes to which rotational state belonging to n equals 1. In that case, it is called rotation vibration spectrum because the transition will involve both n and l. We will discuss it in a while. So, in which range of frequency it will appear, then it has to do with this h bar omega value or h nu. Or in this week's sample question, I'll show you how the spectroscopists label this energy difference in the unit of centimeter inverse, which is the wave number. But let's stick to Hertz or just a frequency. So diatomic molecule is like 2 balls with a spring, and this is a year 1 mechanics problem. You know the characteristic frequency is the spring constant K divided by the reduced mass mu square root. you plug in reasonable number for the reduced mass, and then the ballpark range is infrared, then you have an idea of what is this spring constant. The table here shows you a number of diatomic molecules. So when you see hydrogen in it, the reduced mass is dominated by the lighter hydrogen mass. And the frequency that correspond to h bar omega is around this range. Okay, 10 to the 13 hertz. Well, of course, the number in front vary from molecule to molecule, but the ballpark range is just 10 to the 13 hertz, which is in the infrared. It is about 0.2 to 0.4 electron volt. You can convert it by some formula, or if you go Google, there are some calculator in converting from one unit to various other units. You just key in 0.2 eV, it will return many other things for you. And the force constants, again, typically you see is about 1,000 Newton per meter for the spring constant in a diatomic molecule. So this is what we are referring to, the vibrational mode. The electron set up this binding curve, and then last time we put back the nuclear motion, and now we are analyzing the effect on the spectrum due to this internuclear radial motion, which can be well approximated by a harmonic oscillation. But there is a requirement that for a molecule to show this vibrational spectrum. Now, first of all, the molecule needs to have a permanent electric dipole moment, but that is not sufficient. Another condition that is a key physical concept of this vibrational spectrum is that the molecule, as it vibrates, needs to have a varying electric dipole moment. The reason is very quantum mechanical, but we have all the background to understand it. So these are vibrational levels, thereby they are harmonic oscillator wave functions. So we have a harmonic oscillator labeled by M, which is the wave function that you learned in the last term, only that it is vibrating about R0, which is the equilibrium separation. So we know the wave function here, oscillator state, we know the wave function for another state, higher state, and prime. Now, we invoke the electric dipole mechanism, which has to do with an energy, interaction energy between the electric dipole moment that is matter molecule here and the incident field, which is light. So we have discussed this matter-light interaction problem. The context is time-dependent perturbation field. So we have to explore when this integral is not zero, okay? Now, in addition to that, there's some angular integral to multiply into it. We have discussed that in the rotational part, so we will focus on this vibrational part. Now, if the molecule only has a constant electric dipole moment, then this constant can go out of the integral, and therefore you have a very simple interproduct between two oscillator state labeled by two different quantum numbers, n and n prime. And you know from last term, these oscillator states are orthogonal to each other, okay? So thereby, if this is just a constant, there's no fun. This integral is zero, okay? Now, therefore, what we can do is let it vibrate and then see how this thing in a Taylor expansion looks like as the molecule vibrates. Okay, so here is the Taylor expansion. The electric dipole moment takes on its permanent value at the equilibrium separation. However, as the molecule vibrates, the first order expansion has to do with whether the electric dipole moment would change with R. That is to say, as the molecule vibrates, will the electric dipole moment varies? Okay, if it does, this prefactor is not zero, and then it will multiply into a R times R minus R zero term. Now, if you have this R minus R zero term in the middle of the integral, now that is like oscillator state n of x, and x in the middle, oscillator state n prime on the left. And that is an integral you did in problem set number 2. Okay, I checked it yesterday. And you know, there is a condition for the integral not to be zero, which is delta n ought to be plus minus 1. And that is the selection rule. But on top of it, there is a requirement that this coefficient is non-vanishing. It's not zero. Okay, so the physical context is that as the molecule vibrates, the electric dipole moment varies, changes, and then this term will not be zero, and then you have this vibrational spectrum. Okay, so that is the summary. And now let's look at some two important molecules for your generation. The first one is carbon dioxide. It is a linear molecule. What we mean is that at equilibrium, this carbon is in the middle, 2 oxygen, one on left, one on the left, one on the right. Okay, so it is like this classical mechanics problem that you did in your year 2 course, right? 3000 level, but many of you took it in year 2. So this is normal mole analysis. You can write down Newton's law. The motion could be in 3 dimensions, although the molecules start off as a linear molecule. Yeah, but what I mean is that the molecule could go up and down, not only along the line or into the screen or behind the screen. Okay, so that is a 3-dimensional mechanics problem, started off with 3 balls and 2 springs on a line. So after you do all this, then you will get 4 normal mole frequencies. Let me give you a 30-second summary of normal moles in mechanics. So you write down the Newton's laws. They are in principle coupled because when this mass moves, it will stretch this spring and then compress this spring, thereby all the masses appear, F equals ma, all the things appear in the equation of motion of m2, okay? And thereby you can also write down the mass on the left, the equation of motion on the left, and then on the right, okay? So you have this equation of motion. Then what are normal moles? Well, normal moles basically all the masses vibrates, but with the same frequency called normal mole frequency. So you started off with a coupled Newton's law. You try to do this analysis to look for how many different frequencies you could have, okay? And then you will find the normal mole frequencies. Conceptually, each normal mole, meaning this particular omega, all these masses are vibrating, one vibrational wave is independent of the other normal modes. So they are independent, one has nothing to do with the other. Now go back to the mathematical analysis of normal modes. So you let the molecule vibrate at any time, take a picture, the way that it is moving could be written as a linear combination of this independent normal modes. Okay, so that ends the discussion on mechanics. So in carbon dioxide, there are 4 normal modes oscillation. So here the picture tries to depict the 4 kinds of motion. So for example, this 2, there are 2 here because you can go up and down or in and out of the monitor. Okay, so these are called symmetric bending. You can imagine how the motion is. Okay, and then you have this symmetric stretching. So it's like the carbon in the middle is not moving. The 2 oxygen is going out, in and out, something like that. Okay, and then you have this asymmetric stretching. Okay, so the oxygen on this side is going out, and then these 2 come closer to each other, and then this carbon will go oscillate to this side, and then this will come together with the carbon. Okay, so these are the 4 vibrational modes. As we discussed on the last page here, a criteria is that as the molecule vibrates, the electric dipole moment changes. So let's examine whether these 4 modes are they so-called infrared active. Infrared active means as the molecule vibrates, the electric dipole moment varies. Okay, now it is easy to see that these 2 actually, they are infrared active, right? Okay, so you can imagine carbon is slightly positive, the 2 oxygen is slightly negative. So when 1 goes up and 2 goes down, and then you have this electric dipole moment vectors, you add them together, there is an electric dipole moment coming in the vertical direction, and then when the 2 things go up, so this moment will point in the negative direction. So as this vibration goes on, the electric dipole moment will be pointing up, strings to 0, pointing down, strings to 0, pointing up, strings to 0. Okay, so you have to look at the picture and try it out. Okay, but it's not difficult to see that the symmetric bending one has varying electric dipole moment. Now there is one that doesn't have a varying electric dipole moment. Okay, now so this one, symmetric stretching, again, think about it, it just go in and out, in and out. Okay, so the electric dipole moment always cancels. Okay, so this is infrared inactive. The normal mode frequencies can nonetheless be calculated. And then this one is also infrared active. Here I give you the normal mode oscillating frequency in various units. So in wave number, this is 667 centimeter minus 1. Okay, it means that in 1 centimeter there are 667 wavelengths. So it's just a way to express the wavelength, but in a funny way. So if you want the wavelength is 15 micron. This one is also infrared active, but at a different frequency. So I label all this, okay, for you. In particular, take note of this one, okay, 667 centimeter minus 1. So here is a low resolution carbon dioxide spectrum in the infrared. So here you see two dips in the transmission. So light is absorbed by the carbon dioxide molecules. So if you look at the wavelength, this axis is the wavelength, and it is in a funny scale because originally it's not in this scale. So there are so many units that the experimentalists use. So I just label it for your convenience. So this one here is 50 micron, and then it is 667 centimeter inverse mole. It is this one, okay? So this is symmetric banding, and then the other one is the asymmetric stretching mole. Another molecules that we will discuss is this water molecules. So water molecule is not linear. So at equilibrium, nothing vibrating. It is a O and then 2H, something like that, okay? So it's not a linear molecule. Then you use your classical mechanics idea, count how many degrees of freedom that are available for vibration. Then there are 3 of them. And this here, the picture shows the 3 vibrational modes. So again, you have a symmetric banding. So this will go up and down, and then this one will something like in a diagonal way, go up and then go down and so on, okay? And then you have a symmetric stretching, and then you will have asymmetric stretching. So you can use your head and hands and try out to get a feeling about what these vibrational modes are about. Well, I believe you have done this kind of exercise in your mechanics course, but at the end, it is better to get a sense of what these vibrations are about, okay? So at that time, when you learn it, you might not have any sense about how to apply them. Here is a good applications. So now, if you think about the electric dipole moment, as these atoms vibrate, then you will see that all of them are infrared active, meaning all of them has the electric dipole moment changing as the molecule vibrates. And here, I also give you all the wave numbers, the wavelength in units of wave number as well as in ordinary length. It's good to have a sense of the ballpark range, okay? This is infrared. So here is the water's vibrational spectrum. This is transmission, so we look for the dip, okay? As it comes down, it means at that particular frequency, carbon dioxide absorbed. So here, indeed, you see a big dip here, another one here, and then some other effects. Okay, so if you look at this, this is centimeter inverse. So you have this about 1600, and then you have something around the 3700. So you have a very broad thing in that is 3.5 something, 3.7. Let me see. Okay, so 3600 wave number. So this is about that one. Okay, therefore this actually is contribute. Why some dips is that has to do with the integral. Well, in theory, that has to do with the integral absolute square. There is question about whether this peak is steeper, so it is a stronger or weaker absorption. Get that? Okay, so it is within our theoretical scope actually. Okay, because it is time-dependent perturbation field. Okay, and then you have this one. Let me see, it's about 1,600 or so. Okay, so it is this one. Okay, so you see, classical mechanics actually works. Now, why do we care about the carbon dioxide and water vapor, water molecules? Because they are now regarded as bad guys because they are greenhouse gases. So what does it mean to be a greenhouse gas? So basically, the idea is that the sun, the surface of the sun is about 6,000 K, and then black body radiation is of this form, but it varies with the temperature. So at this temperature, there's a big peak here, I think in the visible. That's why on Earth, many animals have their eyes adapted to looking at this range because the incoming natural light has a peak there. Okay, so we have this from visible on, slightly ultraviolet comes in. So it is short wavelength light comes in, and then on the Earth absorb it, and then after that the Earth surface temperature is about 20 degrees Celsius. You take into account of the ocean, everything. Okay, so the Earth has a temperature like this, so it also does black body radiation, but at a much lower temperature. That is the surface average temperature on the Earth. Therefore, the peak is now a little bit warm. This is warm, right? Okay, it's like today. Okay, so you don't feel very cold, you don't feel very hot, so it's warm. Warm is infrared. Okay, and therefore the peak is around this number. Okay, so that is what the climate people says, or the earth science people said. Okay, long short wavelengths comes in, and then long wavelengths go out. And now one can fly a satellite outside the atmosphere and then measure the emission. So the black curve on this picture refers to 20 degrees centigrade black body radiation. That is to say, this is the expected or the ideal black body radiation from the Earth. But of course, we have the atmosphere. And therefore, if there are molecules in the atmosphere, the long wavelength emission from Earth, some of them will be absorbed by the molecules in the atmosphere. So let's look at the major absorbing molecules. So compared to this line, let's look at the deficient. Okay, so what is less than expected? So suddenly you see there's a window here. Okay, so this window, look at the axis, is about 600 something. Okay, in wave number. All right, so this is the 667 centimeter inverse carbon dioxide, one particular mole. Okay, and that is the major contribution to the trapping of heat. There are others, of course. Okay, for example, you see there's a broad thing that here from water vapor, and in here about 1600, there is a mole due to water vapor. I mean this one here. Okay. There are other things also. N2O also responsible for some absorption. Okay, now absorption from the molecules in the atmosphere is not something bad. It keeps us warm, and therefore life could flourish. But too warm is a problem. Okay, so that is why, you know, every year there's some big event calling for cutting the emission of carbon. And here is some number over 170 years. Well, as long as we have record, and this is how much carbon dioxide are there in the atmosphere. Okay, so you see that it is increasing, especially starting from the Industrial Revolution, when people start to burn coal and then later on fossil fuels. Therefore, it's not surprising that there's a lot of research going on about controlling carbon production or carbon emission, basically. So there are different philosophies. One of them, very popular one, is to reduce carbon dioxide production. And then there are other philosophies say, how about we just reduce carbon dioxide emission into the atmosphere? We can still produce it, okay, but reduce emission. Therefore, how to reduce emission and yet continue to produce them? Then people start to think about how to collect this carbon dioxide as it is produced in a factory, and then find some way to store it. So underground, for example, and then it's not emitted into the atmosphere. So this effect could be controlled. So if you Google carbon capture, carbon storage, there you will find a lot of ongoing work. So there are many different ways to approach the problem in science. And you should also appreciate how lucky we are that you know, these two things is 98%, right, in the atmosphere, nitrogen and oxygen. But you know, they are homonuclei, so the same atom. So therefore, no matter how they vibrate, they are not infrared active. So we are not too warm, at least. Okay, so we are only concerning with a minor component. Of course, water vapor is also a problem. Methane is also a problem. N2O is also a problem. So this is the end of this part. Then we have a shorter last part of the discussion on molecules. So this part is the last section of our module. It is about vibrational rotational spectrum. So basically, it appears in the infrared, but now you have high resolution. Thereby, when we consider the transition, we could see clearly from which rotational state belonging to the n = 0 vibrational family that the molecule goes to which rotational level in the other family belonging to n+1. So there is a transition between different n's. So it's vibrational, first of all, but then the resolution is high enough to see whether it goes from L equals 1 here to L equals 2 there, because there's a delta L equal plus minus 1 selection rule, right? Rotational, the angular, the YLM theta phi integral, okay? So that when you can see that clearly, the spectrum shows up as vibrational rotational spectrum of the molecule. So take-home message is still appear in the infrared range, say 0.1 eV, but then you are looking in this energy scale details or features that has to do with microwave range. So it is like you have a meter that you can see 0.1 meter, but then your meter stick has fine division so much so that you can look into 1,000 to 1/10,000 of a EV, okay? So that is the kind of resolution, well, not very difficult in nowadays labs. So let's look at what will be the structure of this vibrational rotational spectrum. So the idea is that you have an n equals 0 family, okay? And then you have an n equal 1 family of rotational state and so on. Now, again, room temperature, most molecules are in the n equals 0 family, but they can populate different rotational state, okay? Because room temperature is 1/40 eV. Room temperature is very difficult to excite this kind of transition. However, room temperature is okay to excite the molecules to populate different rotational levels. That is the beginning of our story, all right? Now, according to the selection rules, if you start with n equals 0, L equals 2 here, the molecules can go to two different places up. Delta L is plus minus 1. So start from L equals 2, it could go to the upper family, L equals 1, or the upper family, L equals 3, okay? Now think about this particular transition. If the molecule can go from L equals 2 to L equals 2, which is not allowed, okay? If it could, then we will expect a signal that is equal to h nu or h bar omega, right? But this is not there because you cannot, this cannot happen, okay? So you expect to see a line missing in h bar at h bar omega. Then you have one that goes higher in energy than h bar omega. Then you have one that goes lower in energy than h bar omega, all right? So that is the phenomena, right? H bar omega, that particular place, the resolution is high, then you don't see a line there. Then from that missing point, on the left, on the right, you start to see something. Now you can do the analysis. You can take the allowed energy for a molecule and then plug in the two selection rules. Then what you find is what we just discussed. You will see a bunch of equally spaced lines on the right-hand side, I mean higher energy side of h bar omega. You will see a series of equally spaced lines on the left-hand side or lower energy side of h bar omega. Nonetheless, you don't see a signal at h bar omega due to selection rules. So what does it mean? It means this particular form. Okay, so here is an example of HCl, hydrogen chloride molecules. So let's look at the structure. First of all, some, well, at least look quite evenly spaced peaks. This is absorption, all right? So now, but suddenly, it seems to be there is a line here missing. So there's a gap here. Do you see that? Okay, it's not there, all right? Now, therefore, if you read the frequency out, that will be the frequency corresponding to h nu or h bar omega, because that is the place you don't see a signal. Get that? All right. Now, if you can read that out, you already get omega. And therefore, omega is K, the spring constant divided by reduced mass square root. So quite nice. You can read that out and then calculate the spring constant of the molecule, which is another property. Second thing, if you read out the spacing between neighboring peaks, it is just the rotational spectrum idea. This spacing is related to h bar square, which is constant, 1 over the moment of inertia. Therefore, you read that space, equally spaced line, you read that difference out, you can calculate the moment of inertia, thereby the bond length. So let me summarize. Rotational vibrational spectrum typically goes like this. This is a very clean one. You can imagine if I have a poly nuclear molecule, so that is to say a polyatomic molecule, I have 6 atoms forming a molecule. There will be many vibrational modes. Maybe some of them have overlapping frequency, thereby the spectrum will be more complicated than this one, okay? Nonetheless, we are just trying to demonstrate the concept. So when you have diatomic molecules, and if it has, it is infrared active, therefore, you can read out the missing line here, get omega, okay? And that will give you the spring constant, and then you read out the spacing between these equally spaced peaks, that will give you moment of inertia, thereby give you the bond length. Here's another transmission example. This is hydrogen bromide. Again, there should be something here, but not there. Okay, so you read that out. This is h bar omega. You get omega. You get spring constant. Then you read this spacing out. You may read this one and divide it by 4. Read this one and divide it by 5 because you have 5 spacing there. Okay, and then you can get the bond length through the moment of inertia. All right. Now here in this figure, to help you out, it is labeled with the transitions between L. Okay, so 0 to 1, it is 0 here to 1 there. So this particular one is longer than h bar omega. So it is this particular dip. Get that? Okay, so to help you out, this figure on the left-hand side refer to such labeling on the rotational vibrational spectrum. Okay, so schematically, to simplify things, the spectrum is something look like that. Of course, that will throw away a lot of details, but basically it is something like that. So you read this thing out, you get that, okay? Again, you read the spacing out, you get moment of inertia, all right? Now, some technical jargon. This side of h bar omega is called the R branch. This side is called the B branch. Okay. So the next 2 pages, I just illustrate how to get the number for you. So depending on, pay attention, this is physicist exercise. So this picture is very friendly, EV, but more often you see frequency, or sometimes you see centimeter -1. So be careful. So this one is friendly for us. So you just read this thing out here. Okay, so around there, then you say 0.316 or 7. So maybe so that is the gap. Okay, and we know the meaning of this. This is just h bar omega. All right. Therefore, we know omega is also this hydrogen bromide. So the reduced mass has a formula to plug, but when we see hydrogen, then we become lazy. So this lighter mass dominate. Therefore, it's about that. Okay. Well, you can do it more accurately. Therefore, we can calculate the spring constant by reading out the omega, and you calculate the spring constant. Okay, now this is another unit of the spring constant. You can convert it in Newton into Newton per meter. Next, go back to here. We want to identify what is this spacing. So this thing is about from here to there. Okay, or you can do it like reading out several of them and divided by 4, for example, here. Okay, then you can read out that it's about 0.002 eV. Now that's the resolution you need. Okay, what this happens, okay, this whole thing happens at around 0.3 eV. So on this scale, we are reading out things like this 100 times or even smaller than that. Read this thing out, and we know this spacing is h bar squared divided by I. I is the moment of inertia. Therefore, moment of inertia can be calculated by reading out the spacing. Okay, and we know the moment of inertia is related to reduced mass that we calculated, and the unknown is the bond length. Therefore, plug everything in, the bond length can be calculated. Okay, so when you read out the spacing, plug it in, you get some very reasonable number. It's 1.4 angstrom. That comes together with our quantum mechanical discussion, right? LCAO. You need the atomic wave function from the two atoms to have some sense of each other. So they must touch each other, the wave function. And you know, wave functions decay quickly from the nucleus. So 1 angstrom or something like that. So when you calculate something out, the bond length is 1.4 angstrom or 0.14 nanometer. It's reasonable. It makes sense. Okay, if you calculate it out, it's 50 angstrom. Probably you make a mistake, right? So that's the end of the vibrational rotational spectrum discussion. So let me quickly summarize this whole module for you. So for molecular spectrum, we have this vibrational state in many more of them, okay? And this difference is typically in the infrared. Room temperature is this number. So usually molecules reside on the n equals 0 vibrational state. Belonging to the n equals 0, there is a family of rotational level, and KT, room temperature, could populate the molecules according to statistical physics, a Boltzmann factor. Then matter-light interaction, but this time it's molecule. Again, it's electric dipole mechanism that we are considering. Then there will be selection rules. Rotational spectrum, the transition is between this rotational state only, has nothing to do with this family it occurs in the microwave region. Equally spaced line will appear, and then you can read that space out, and then you can get moment of inertia, thereby you can extract bond names. In the infrared resolution high enough, we can see vibrational rotational spectrum, very nice picture. This is the fingerprint of a molecule, okay? One cannot mimic the other. It's like an atomic spectrum. So this molecular spectrum can identify molecules for us even if we can't touch them. Therefore, in astrophysics, it's a very popular thing. I would like you to Google today's science news. I think there is a new development in astrophysics. People are looking at a funny molecule called HD, hydrogen with a deuterium. So it's an isotope, okay? So, well, of course, in the early days of the universe, the abundance things are just hydrogen or helium, okay? So I think there's a new important piece of work for identifying HD molecules to study the early universe. Just come out yesterday. And then the application is obvious. We can study properties of molecules, extracting spring constant and also bond names. Therefore, we can use them to identify molecules out there, places that we cannot touch, and we could understand the quantum mechanical origin of greenhouse gas, although knowing the science doesn't help. It's still warming up, okay? There are many Nobel Prizes awarded to this kind of work. So, I mean, in molecular spectroscopy only. So Herzberg from Chicago, and then some laser spectroscopy. When laser was invented, the whole thing of spectroscopy, basically every molecules must be restudied again, right? Because the resolution is higher, the signal is stronger. The last thing is that, what if a molecule is infrared inactive? So all our tools become invalid, okay? Don't worry, there are other spectroscopy methods, for example, Raman spectrum, that could help us through. But we will not discuss it here. So even very recently, there's some new Nobel Prizes in the life science side, okay? So they could go down to resolution of a single molecule. A very clever thing in using physics. So at the end here, I just give you some very specific spectroscopy references, because at the end, if you are doing experiments in condensed matter or AMO, basically high precision spectroscopy is a topic that you cannot escape. So therefore, you have some rough background here, but if you want to go into the more details into the topic, here are two readable books at your level, okay? So very similar titles, Atomic and Molecular Spectroscopy. I think this one, you know more than half of this book already. You take a bird, flip, and then you know that, okay? Don't read from page 1 again, okay, CUHK students, okay? You have some background, cut in, get what you want to know. This one is deeper, so therefore, you only know 150 pages out of this 500 pages book. If you want some expertise to help you out, Professor Wang Dajun in the department is an expert in high precision spectroscopy. So some final remarks. We haven't talked about, and we are not going to talk about this particular transition, is from one electronic curve to another electronic curve. This is called electronic transition. Well, for electronic transition, first of all, some idea, usually you need ultraviolet light. So much higher energy than what we discussed. And then usually there's no selection rule, everything goes. And that's all I want to say. So this is some electronic spectrum. So for the whole module of physics of molecules, here are some references. We are above the level of the first one. So this is a very nicely written quantum physics or modern physics book. The physics content is very rich, but our treatment in quantum mechanics is of higher level than this book. But if you want to read about the physics, this is a good one. The second book, I have it here, something like that. Okay, physics of atoms and molecules. It covers more than we did. If you want to really get into a higher level or the beginning postgraduate level of atomic and molecular physics, this is a very readable book. And then, because atoms and molecules basically has to do with chemistry, this is a very nice book, Quantum Chemistry by Donald McCurry. It is supposed to be for beginning postgraduate student in chemistry. But if you have time, I think there's a copy reserved in the library. Go there, take that, and then flip over them. I think if you open up your mind and yourself a little bit, you will see that you know 90% of this book. You are still year 3, okay? So physics students really have some advantage in doing theoretical chemistry or quantum chemistry or physical chemistry. The same author has another book called Physical Chemistry, a molecular approach that covers quantum chemistry. In addition to that, the author also did thermodynamics, statistical mechanics, and also chemical kinetics. Together with quantum mechanics, these subjects cover the field of physical chemistry. That is to say, by this time, I think you are also ready to get into research or a postgraduate program in physical chemistry, okay? So keep that in mind. Don't restrict yourself too narrowly. Maybe next year when you plan for graduate school, this is another option. There's another competing book, competing with McCurry, Engel, Quantum Chemistry and Spectroscopy, very nicely written with many colorful pictures, okay? You know, chemistry book is much more friendlier than physics book. Everything is printed out, orbital, S, P, D, okay? Very colorful pictures, okay? In physics book, Y21 theta 5, a long formula. You don't know what it is, okay? Very specifically, but very simple book, Molecular Spectroscopy, very thin book in the Oxford Primer for Chemistry series. In about 80 pages, you will be introduced to all the things about molecular spectrum, okay? So that ends the whole module. And let me announce that this is the cutoff point for the final exam content, okay? Don't tell the student who don't come, okay? And then we will have a break now. So there's the question, a long question. Let me read it and see what happens. The last time we have mentioned how populated state will also affect the intensity. Yes. So the final intensity is actually related to high density Boltzmann. Okay, so let me read let me see, a very long one. So the student says,